All right, so there's a change in the, I'm recording now. There's a change in the lab schedule. The class agreed that they'd rather have a long lab this week, right, and no lab next week. Okay, so labs 15 and 16 will be done this week on Wednesday, Thursday. So you need to have your pre-labs done for both 15 and 16. And they're very similar pre-labs. Like the first aid is going to be for sodium hydroxide. And that's it. Okay. So let's continue with solutions. Now we started talking about solutions last week. And this is what we covered. We talked about how you measure concentration of a solute in a solvent. We did that with something called molarity, moles per liter. So again, moles is really fitting into everything chemistry related, physics related also, geology related, biology related, molecular biology particularly. Okay, so this is a typical problem. Let's review this. Okay, what's the molarity of the following solution? 34.5 grams of sodium chloride and 3.45 liters of water. Okay, so the definition of molarity is moles of solute per liter of solution. That's the official definition. Now, so we need to get moles of solute. I gave you grams of solute. We need to convert the grams to moles. So the first thing is using the molar mass of sodium chloride, 5844. And that is going to go here. And that answer is now, and a student in here last week said, you said 33.45 liters of water. But when you put salt in the water, it's not going to be 3.45 liters anymore. It's going to be a little bit more. So what we have to do is we have to make an assumption that the change when you add the solid in there is minimal. Okay, does everyone understand what I'm saying? Like when you sit in a tub, what does the water do? It rises. So when we put anything in water, it's going to rise a little bit. And the question is that going to matter, that little bit? Okay, and we're going to assume it's not enough to make a difference. Okay. All right, and then we just divide out. So the concentration of that salt in that much water is going to be 0.180 moles per liter. Yeah. I'm sorry, where? Well, did I punch in the wrong numbers? Oh, I put in 55.44. Given. Yep. See it up there? Three. Right there. And that 58.44 is the molar mass for sodium chloride. So what did you get? It helps to put the right numbers in. Okay, that's my mistake for today. I always make at least one mistake, usually many. All right, is everyone okay with that? Huh? Okay, then there's the opposite. If I told you a certain concentration of a solution in so many liters, how many grams of solute are there? So we're working backwards now. Okay, so that 3.45 M means we have 3.45 moles in 1 liter. We don't have 1 liter, we have how many liters? 567. So if we multiply that by 567 liters, we'll find out how many total moles we have. Okay. Now we're going to convert moles to grams. So 3 sig figs, 1140 grams. No, it's 11. Because I got 1.14317. Now I used all, if you use, go back up to here, because I rounded to 3 places here. But see, I used the number before the rounding, the 19.6. And see, because, and that rounds up to 6. Look at the, do it. Same thing. Your point's well taken though. All right. Okay, so these are the dry measurements. Because there's 2 ways to make a solution, with dry ingredients and with liquid, concentrated liquid. So that's done very, very commonly in the stockroom when we order acids. As we order very concentrated acids, then we dilute them to a certain concentration for the labs. We never order dilute acids. They're too expensive, way too expensive. So all the lab people have to make calculations based on how many liters of solution they want for the labs and at what concentration. And secondly, what are you starting with? What concentration are you starting with? So what I'm going to do 2 more examples of dry solution. I'm sorry?
It depends. I mean, there's
It's either 1150 or 1140. If you take, when you do this calculation, and you use that number here, you get 1140. If you use 19, I'm looking at this website, yeah, you'll get 1150.
I got 1150.
Does that make sense?
Yeah.
Okay, so let's do a couple dry again. Okay, so okay, so how to make 23.4 liters of 4.56 molar hydrochloric acid, HCl. Let's not do HCl because that doesn't come dry. Let's do lye. Sodium hydroxide comes dry. Okay, so what do we need? Making up a solution with dry ingredients, we need to have a certain amount of grams of sodium hydroxide in so many liters of water. So how do you think we want to do that? Huh? Okay. Right now we have I'm going to convert the M to moles per liter. We want to know how many total moles are in there. So if I multiply that by 23.4, that'll be the total moles of sodium hydroxide. And I'm going to go ahead and use the rounded one. So that's 107 moles of sodium hydroxide. How many grams is that going to be? Well, okay, sodium is, what's the molar mass for sodium? 2299. Oxygen 16. Hydrogen is 101. So we are looking at 40 grams per mole. So 428. Okay, the question says how to make. We're not done yet, because I need directions on how to make that solution up. Now, if you're working in the lab, this, what I'm going to say next, is extremely important. Okay, so there's two scenarios. If I put 23.4 liters of water in one container and then dumped in 428 grams of sodium hydroxide, will the volume 23.4 stay the same? That's right. What will it do? It'll rise up. So what we're going to end up with is a more dilute solution, because the solution is no longer going to be 23.4 liters. It's going to be more. It could be like 30 liters. Okay. When we add in a tiny bit, it doesn't change much. When we add a lot in like this, 428 grams is a lot. It's almost a half a kilo. It's a lot. So the water is definitely going to come up. So the way to do it and keep it at 23.4 is to start with a small amount of water, like something less than 23.4. Let's say 10 liters. It doesn't matter as long as it's below 23.4. Then I'm going to dump in the 428. And mix it up till you cannot see it anymore, till it becomes a homogeneous solution. When it's totally dissolved, then we're going to bring the final volume up to 23.4 liters. Exactly.
You said it was fine as long as it was under 23.4 liters for the 10.
It could be 22. It doesn't really matter, as long as it's below that.
So let's say it's 23.3. I could still add 420 grams.
It depends. That's getting kind of close.
Right. Okay.
So you have to be far enough away so that when you add it in,
I see what you're saying. Gotcha. Okay.
And this is the official way. Now, as a professor seeking employment here, there's two things you got to do. One is an interview, and the other is you have to demonstrate lab technique. One of them is making up a solution, and this is what they're looking for. Exactly this. So all new hires, faculty members and lab techs both, have to mix up solutions. They also have to do what you're going to be doing on Wednesday, Thursday of this week, a titration. Okay, so does this make sense? How we mix it first and then bring up the final volume to where it's supposed to be? Okay, and let's do one more dry problem. Okay, if I dump in 345 grams of sodium hydroxide and 234 liters of water, what's the concentration? Okay, so this is a two-step problem. First is calculate the moles added, and then you convert that to moles per 1 liter. So first one is sodium hydroxide. Okay, so the molar mass of sodium hydroxide is 40. So we have now notice I'm adding the .00. If you just put 40 down, that's 1 sig fig. 40.00 is 4 sig figs. Big difference. So make sure you carry through with those zeros. I'm sorry, what? Yes, that's right. But you still need to put in the precision that you were available based on the periodic table. Yeah, the answer is going to be 3 sig figs. Another question, do you need to put the .00 in your calculator? No, you can put it in there, the total waste of keystrokes. So when you put in 40, your calculator assumes it's 40.00 zero, 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 zero to 29 places underneath the keyboard. So don't waste your keystrokes putting in .00 unless you have an OCD complex. Then put in .00. I know a lot about OCD. My second wife was OCD. That's why she's my ex-wife. And all this is over 234 liters. Okay, so those are the two variations on dry ingredients. Yeah.
You might speak up.
Oh, you mean like that? Now, I've got lots of practice for you when you go to Files, Unit 5. Huh? Yeah, I'm going to go there in a minute. I have a whole bunch of molarity worksheets, a whole bunch. I have a couple on making dilutions. And then worksheet on titrations. We haven't talked about that yet. That's what your lab is going to be this week, titrations. In fact, I should probably cover that now. Yeah, do titrations now. Okay, so let's do okay, your lab this week is called acid-base titration. So the first thing we need to talk about is what is an acid and what is a base? Acid you've probably all heard of. Who's heard of a base before? Okay, couple of you, few of you. Who's heard of alkaline before? About the same group. Okay, alkaline is an old name for a base. It's still used fairly often. But whenever you hear alkaline, think of base as well. They're the same thing. Okay, so when I say base, what does that mean? Okay, base is a compound. Okay, is a compound that will disassociate an OH ion, hydroxyl ion. So for example, sodium hydroxide, does that have an OH on it? Sure does. The next you need to ask, is it come apart? Does it disassociate from the sodium? Yes, it does. And if it's a strong base, 100% will come off. So in a strong base, sodium hydroxide Li is a very strong base. So when you finish mixing up a sodium hydroxide pellet, there's no powder left. That's because all the NaOH has become into ions. So this is going to be aqueous, totally dissolved. Now, and that's called a strong base. So so 100% ionizes. So weak base, 1 to 99% ionizes. So notice the arrows. In a strong base, there's only one arrow. That's because there's no two-way about it. With a weak base, part of it ionizes and the remainder remains unionized. Okay? Now that's a very important distinction. There are very few strong bases. There's sodium hydroxide, potassium hydroxide, and some of the alkali earth hydroxides are also strong. Most bases are weak. There's probably 1 million or so weak bases, particularly in the biochemical realm. Okay, and then there's the last category, a non-base. For example, drinking alcohol. Ethanol, got a hydroxide group on it, an OH group. The question is, does it disassociate? No. Oops. So that doesn't happen. Now, the reason why we have strong, weak, and non-bases is for stability reasons. How strong is what you start with versus what you end with? In the case of ethanol, what we start with is very stable. Very stable. So when they want to pull out that OH group, what becomes fairly stable becomes very unstable. And that instability is what makes it a non-base. So if what you're trying to produce is something very unstable, it's not going to happen. With sodium hydroxide, that sodium hydroxide compared to what is made is horrendously unstable. That's why it wants to do that. Very happy in a water environment. Then you have everything in between, the weak bases. Okay. Now these are test questions. What's the difference between a weak and a strong base? One ionizes 100%, the other one doesn't. Same with acids. You're going to have strong acids and weak acids. Same thing. Okay, so that's a base. Let's look at, are there any questions about what something's alkaline or when something's basic? Same thing, that's right.
Base and basic, same thing as well.
Basic. Yeah, something becomes basic with a base. Something becomes alkaline with something that's alkaline.
So if non-base is unstable, instability makes a non-base a non-base. Instability makes a base a base.
Stability makes the reaction happen.
Right. Gotcha. Yeah.
Okay, so let's talk about an acid now. An acid is sort of the opposite of a base. When I'm done talking about acids, I'm going to show you why I'm saying that. Okay, so an acid is a compound that dissociates a hydrogen ion, H+. So bases are OHs ion, acids are H+ ions. And there are 7 strong acids. In this class, we've talked about 2 of them. HCl, hydrochloric acid, and sulfuric acid. There are 5 more. And those 2 you need to know. So if I should say hydrochloric acid in a word problem, you should say, oh, that's HCl. Okay, so you have now, when you get into 1A, possibly 2A, depending on who your instructor is, they're going to say the H+ binds with water and forms that, called a hydronium ion. Okay, but in here we're just going to leave it as H+. So when they start talking about hydronium, that's what they're talking about. And there's a little reaction called forming a coordinate covalent bond. That's why that happens. Okay, you don't have to know hydronium for our class though, but that's, and then again, it depends on your professor, depends on the textbook. They go back and forth. But classically, the definition of an acid. Now, there's numerous definitions of both bases and acids, but this is the classic ones I've been giving you. Okay, so that means when I say 100% strong acid, that means everything comes over 100%, just like with a strong base. If we look at Then there's weak acids, just like weak bases. Part of it comes off, part of it stays together, like acetic acid, vinegar. That's a classic weak acid. Now, normally weak acids are not written like that. Normally, weak acids are written like that. And this is the part is the acidic part. So weak acids have the COOH as opposed to C2H4O2. And this is the one here that leaves. So one other thing too. Whenever we have a ionic reaction, we always write the cation first, positive one first. So that means the H comes first. It's supposed to be a 3. So this is the preferred one, way to write that. So weak acids have COOH. And look at the 2 arrows. Little arrow said a little bit of H comes off, but not a lot. Big arrow means that most of it is on the left as opposed to the right. Contrast that to strong acid where everything is on the right, nothing on the left. Strong acid, everything disassociates. Weak acid, part of it. And then like bases, we have a non-acid. That is very unstable. So it doesn't happen. Okay, so the question is, does it have a hydrogen? The answer is yes. And that's the most common element in the universe, hydrogen, by the way. So the odds are pretty high that it's going to have a hydrogen. Question is, does it come off? And how much does it come off? And again, there are millions of weak acids in our bodies. Most acids are weak. Now, additionally, we can have things that have multiple OH groups that come off and multiple H's that come off. So I'm just showing you when one comes off. Sometimes there are multiple ones that come off.
Bases of the oh, we. I don't know.
Well, I'll usually tell you it's a strong base or whatever, because there's with your background, there's no way to tell. So, at least in the scope of this class. Okay, so let me show you another kind of acid. That's sulfuric acid. Sulfuric acid is unique because it has two hydrogens that come off. And then we have phosphoric acid. Three of them come off. Now, the three coming off is not very common. Two coming off is sort of common. A lot of organic acids, you can have multiple hydrogens coming off, particularly biochemical acids. Who has heard of the tricyclic acid cycle in our body, or the Krebs cycle?
Oh, yeah.
Okay, that's a triprotic acid. Citric acid is three can come off, or the citric acid cycle, another way of saying it. It's part of carbohydrate metabolism. And if you're in biology class, frequently you'll have to memorize the Krebs cycle along with the glycolysis and electron transport. Particularly if you take a biochemistry class, you'll commit that to memory. And it's about 15 steps long. So it's everything in our body happens very stepwise. If you do stuff and if you have reactions that go a little bit at a time, it's easy to regulate them. If it all goes boom, hard to regulate. So our body is very clever. It decides to take steps really in very small steps. And each step can be regulated. So our body has a lot of control. For example, you get hungry. That means your body is telling you you're low on energy molecules. So the feedback loop is to say to your brain, eat something. That's called a feedback loop. Our body has a whole bunch of those, and that's how it regulates reactions. Okay, so that's what an acid is. Now, there's an interesting molecule that some of you have heard of. What's that molecule? Notice I didn't write H2O, I wrote H-OH. That is water. One of the more common substances on Earth. Very, very common. Okay, notice it has an H and it has an OH on it. And they can come off. So water is both an acid and a base at the same time. And notice the two arrows again. Is that a strong or weak acid? Weak. Strong or weak base? Weak, because it's got two arrows. Remember, one arrow is strong, two arrows are weak. One arrow with an X on it means it's not an acid or a base at all. So definition of an acid is it disassociates an H plus. Definition of a base is it disassociates an OH minus. Both boxes are checked. So water is both an acid and a base. Okay, it's a very weak Now, there's a way to measure acidity and alkalinity or basicity. Okay, that's what something called pH. So pH is a measure of acidity. You've probably never heard of this one, but pOH is a measure of how basic something is. So who has heard of pH? Yeah, almost everyone in here has heard of pH. pH, we're not going to calculate pH in here. We're going to use pH as a measure of acidity. Now, what's weird about pH, the smaller the number, the more concentrated it is, which is counterintuitive to most people, including me. And it has to do with how you calculate pH. The definition is, don't write this down, pH is the negative logarithm of the hydrogen ion concentration. Acidity, pOH, is the negative logarithm of the hydroxyl ion. So you have to know about logarithms and all that stuff. And I'm not supposed to teach about logarithms in this class. That was one of the interview questions, actually. All right. So, however, we can talk about pH without having to calculate it, okay? So, pH of 7 is considered neutral. Notice that says that's less than, I didn't write less than or equal to, less than. So pH greater than 7 is considered alkaline or basic. Like if you ever tested your pool water or your tap water for alkalinity, they'll check the pH, usually with either a test strip or a solution that you compare colors to. There's also a meter that measures pH very accurately, but they're also expensive. So usually we use an indicator, piece of paper that's color coded based on the pH. Okay, now I want to close today I'm going to close by talking about the concept of neutralization. So we mix an acid and a base. What happens is the H from the acid and the OH from the base produce what? What does H plus OH equal? Water. So when you have a neutralization reaction, you make water plus what's ever left over. So what's left over after you take out the H? What's ever left over after you take out the OH is the salt left over. So this classic neutralization reaction. Acid plus base gives water plus a salt. All the time, no exceptions. So let's look at strong acid, strong base, gives us water, plus what's left over. Well, the sodium's left over and the chloride is left over. Sodium is positive, so that goes first. Chloride is negative, it goes last. We took a sulfuric acid, notice I put two NaOHs because there's sulfuric acid. I mentioned there were two H pluses coming off. That means we need two OHs to neutralize the two H pluses. That gives us two waters plus the salt, sodium sulfate. Because we have two H's and two OHs coming off. Each one forms a water. Now, this is what we're going to do on Wednesday, Thursday, the lab 1516. We're going to do neutralization reactions. Okay. Tomorrow, I want to talk about something called titration, which is the essence of the labs we're doing this week, and it's a neutralization reaction. We are going to calculate how strong a vitamin C tablet is for lab 16. Okay, so that's what I wanted to cover today.